In this video, I introduce a stochastic backpropagation in reparameterization trick. Generative deep latent Gaussian models consist of Gaussian latent variables at each layer, and the generative process is written as here and explained in this figure. Where CL are independent Gaussian variables, TL are multi-layer perceptrons, and GL are matrices. Gradient descent methods require computing the gradient of expectation of a loss function f with respect to a distribution q theta, assuming f is integrable and smooth. Computing the expectation is difficult since the expectation is dependent on the indirect distribution q theta. If the distribution q is selected to be a Gaussian, the gradient can be computed by using the Gaussian gradient identities as shown here, which are true in expectation for any integrable and smooth function f. For example, using reparameterization trick, z computed from mu, r, and e, and xi is computed from r. The gradient of expectation with respect to r is computed using this formulation where g is a gradient of f evaluated at mu plus r e. As shown here, this forward propagation and this backward propagation. To perform an inference, we need to integrate out the effect of any latent variables xi, namely compute the marginal likelihood. Using Jensen's inequality, the evidence lower band f of the log likelihood is obtained by using this formulation. This evidence lower band, this KL divergence between the variational distribution and the prior distribution. This is a reconstruction error. Where Q is approximate posterior distribution, the problem becomes to optimize the evidence lower band on the marginal likelihood. If the approximate posterior is a Gaussian distribution condition on the observed data, Q factorize across the L layers as shown here, where Vn is a column n of matrix V, and theta r is the parameters of Q distribution. For the Gaussian prior and the Gaussian recursion model, the Q divergence term in evidence lower band can be computed analytically, as shown here, where GRC and C indicate the trace and determinant of the matrix C, respectively. One-column method is applied to compute the expectation above. The gradient with respect to the JS generative parameters, theta, g, and g, as shown here, and a biased estimator of this gradient is obtained by approximating the equation above with a small number of samples from the recognition model Q, as shown here. To compute the gradients of f with respect to theta r, the reparameterization trick is used to write the gradients of f with respect to the mean vector mu and the factor matrix R, as shown here, where this term are computed by back-propagation. The unbiased estimators above are obtained jointly by sampling from the recognition model and updating H in the generative model. The gradients are computed by using this formulation using the gradients above here. The backpropagation is performed by using the gradients in the generative model and the gradients from these two gradients in the recognition model. Here is the deep latent Gaussian model learning summary. First, we get a mini batch V, and then we get a sample from Q, and then we calculate the H from this equation, and then we update the gradients using these two equations. Finally, we update the model parameters theta G and theta R. The same procedure is good for variational autoencoder as shown here. For more details, please check with these references. Thank you. Bye.